Welcome back, and it's been 10 days since students in here had any physics class, so don't judge them too harshly if you're watching this right after you watched the previous video and there was no layoff for you. So anyway, but they just enjoyed a week-long Thanksgiving break plus weekends on both ends, so it's been 10 days. Let's see what they remember, see what we can remember without looking at our notes, but have them readily available in case it's just sad and we need to look it up. But let's see what we remember first of all. We were talking about something called work. And we said work is a transfer of something. If I do work on this water bottle, I have to transfer something from me into the water bottle to do work on it. What do you have to transfer, class? Energy. And how do you know that energy has been transferred into the water bottle? Movement. If it moves, water bottle moves, it has energy. It came from somewhere. It came from me. I gave it energy. I did work. All right, that's enough work for one day. So that's our definition of work. It's a transfer of energy from one body to another as evidenced by motion. We call that, class, work. Now, we said that although work is made up of vectors, work itself is a scalar. So tossing the water bottle this way is not then positive work, and tossing it that way negative work. No, I caused energy to transfer both directions. I didn't just undo the work. I'm doing more and more and more work as I do this. Okay? Lots of work. I'm working hard. Well, I'd be working harder if this weighed a little bit more, right? Like if I were doing that with like a 30-pound dumbbell, just tossing it up and catching it, that'd be actually really cool. Yeah, we'll stick to a 20-ounce water bottle from Walmart. All right, so anyway, what would affect the work that I did? Obviously, I said if instead of a 20-ounce water bottle, if I were tossing a 20-pound dumbbell, that would be more impressive, right? That'd be more work. What would also be more work? Let's say I decided to stick with a water bottle. How could I do more work on the water bottle? Throw it higher, more work, right? And or toss it across the room, toss it further, right? So there's two things that we said affect the work that is done. What are the two factors affecting work done? In a way, because the greater the mass, the more weight it has, therefore the more I have to transfer to get it to move because it requires more force. There we go. More force is needed, right? A 30-pound or 20-pound dumbbell even is going to take a lot more force to toss it than a 20-ounce water bottle. So the more force. Now, I could take the same 20-ounce water bottle and give it even more energy. If I chuck it really hard, even though it doesn't weigh more, if I just applied more force to it, I would cause it to go a greater distance, and that would be more energy transferred. Also, if I chuck this to the back of the room, and I chuck, I don't know, I make a paper airplane, and I send the paper airplane to the back of the room. Well, okay, they go the same distance, right? But one required more force to get it there, right? So more force, but if I chuck the water bottle this high versus I chuck the water bottle that high without hitting the ceiling, well, that's a greater displacement. So we said that work depends on both force and displacement, so that work equals FD. There's our equation, our first equation for work. We'll look at work again in the next chapter. But work is equal to force times displacement. Now, there's two different measures, two different units we can use for work. If we're in the SI, we assume that force is measured, class, in newtons. Hey, that's good. We remember something. And displacement measured in meters. So a Newton meter, when they're in line with each other, force applied this way, movement in meters along that way as well. As they're applied collinearly, we said that a Newton meter is renamed, what SI unit for work? Joule. We said if your husband goes to work one day, he can afford to buy you joules. If he's a lazy slob, don't marry him, but no joules for you. All right, so the joule, named after James Prescott Joule, we'll just abbreviate it with a capital J, is our unit for work in the SI. Now, in the US, we don't measure force in newtons. We would measure force in pounds. How many pounds did you lift, or pounds of force did you push? And displacement's not measured in meters, but in feet. So we said that work could also be measured in foot-pounds. And there's no cool name for that, it's just foot-pounds because we're in the US and we're boring like that. We're like, why would I come up with another name? I already got foot-pound. So anyway, so there's our units for work. Now, I did emphasize a moment ago that the force has to be applied in the direction of motion. So for instance, we said if I push, well, it's going to topple. If I push downward on the water bottle, it slides this way, even though my motion is mostly down, right? My motion's primarily down. You kind of hear it crunching the water bottle. But there's a little bit of motion going forward. That force that's applied in the direction of motion causes the actual work to take place. So here's the question. What if I apply my force this way into the board and the board doesn't move at all? There's force applied, but the displacement is zero. So how much work was done? None. No energy actually transferred. Force was applied to the board, but energy wasn't transferred to the board. We also said that as I'm holding the water bottle, in what direction is my force applied on the water bottle? Upward. In which direction is the water bottle moving? That way. The force isn't in the direction of motion. Now, at this point, the force is in the direction of motion, isn't it? Right? So because force is in the direction of motion, now I'm doing work. But in this case, if I'm just holding it here, even though I'm moving forward, even though the bottle is moving, my legs are what are doing the work. My hand is doing no work. If I did this long enough, my hand would eventually get tired. But it's still not doing any work. Correct? We said this as well. If I set the water bottle down, in what direction is my force right now? Upward. But the motion is opposite. Since the displacement is in the opposite direction of the force, and these are both vectors, one of them has to be considered to be negative. And if one of the two is negative, then work will come out to a negative value. Now, this is important. If I do this, that's force and displacement, that's work. This is also work. Force in the direction of motion. Work, 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 work. Positive work, negative work. Positive work, negative work. And if you added all the individual work together for up and down motion, you get nothing. All right, no work done. It's the sum of all the work. Not true in horizontal motion, but it would be true in vertical motion because of the ability to do negative work. So some different thoughts there. We said if force is applied at an angle, remember, it's not how much force is applied, but how much of the force is in the component that resulted in motion. If motion is up, how much of the component was upward? If it's forward, what component was forward for that motion? And so let's look at a problem with that before we move on from work. Page 171 in your textbooks. Page 171 in your textbooks. It's such a nice job decorating for Christmas. My room's not decorated for Christmas yet. It will be eventually. I'm going to decorate for Christmas. I just think it was a slob. Actually, I was working hard all through. You know, that's what it was. Hard work.
Lifting boxes doesn't work.
No. Well, lifting boxes is. And setting them down isn't work. In fact, setting them down is, and carrying them isn't work. Setting them down is negative work, and carrying them is no work at all. But lifting them is work. So some work was initially done, then countered by negative work later. Carrying them downstairs, more negative work. We didn't carry anything upstairs, just ourselves. Anyway, page 171, number 5. Go and read that for us if you would, Audrey.
How much work is done in number 4 if the box is accelerated at 0.94 meters per second squared? A on a flat surface and B down a ramp raised 20 degrees above the horizontal.
All right, so this builds back on problem number 4. Okay, so referring back to number 4, we had a 75 kilogram box pushed a horizontal distance of 7.35 meters. Now in the problem originally number 4, which we worked last time, 10 days ago, it says the speed was constant. Well, now we're changing it and it's being accelerated to 0.94 meters per second squared, coefficient of kinetic friction 0.35. I didn't move it too far. All right. I'm not OCD or anything. We're looking at the screen like to you guys, this is centered in the room, and to the camera, it's like shifted way over on one side. So anyway, All right, so we've got our free body diagram. So there's the surface. Here's the box. I'm going to draw this along with me. It's a 75 kilogram box. And in our free body diagram, what forces do we need to draw? Weight acting straight downward.
Normal.
Normal force upward supporting the box.
Applied.
There's an applied force. Do we want the box to be pushed toward Michael or toward the periodic table chart? Toward Michael. Okay. All right. We don't know what's in the box. Maybe it's dynamite. Push it toward Michael. And anyway, well, actually, if the fuse has been lit, push it toward Michael. Not, I wouldn't put it. I would give it to Michael. Anyway, too many Looney Tunes cartoons, right? Stick a dynamite and here, Putty Tat, eat this. And anyway, so much violence. I tell you, in the Looney Tunes cartoons. It's what made them so much fun, you know? And now today, no violence is allowed. It's like, what fun is that, you know? I tell you, nobody falling off cliffs, and anyway. All right, clearly I've watched a lot of Looney Tunes. So we have an applied force, and then one more force, friction, which is keeping the box of dynamite from going to Michael, or at least trying to. All right, first force we always find. Weight, which acts straight downward, and if we happened to have done this in the last class, we've already known the weight, but we don't have that still because that was 10 days ago. You still have it? What is it?
Yeah, it's I have 1,890.7.
I have 730.
I have 735
Maybe I
newtons.
have a different weight.
All right, so 735 newtons should have been the weight there on number 4 from the last problem, so that's the weight now as well. Normal force then, class, is also?
735.
Friction force is the normal times the coefficient, which coefficient was 0.35. So how much friction is there?
256.5.
And in the last problem, we said the box was moved at a constant speed. We call that translational equilibrium, remember? And so we said the applied force would also be 257.25 newtons. But that was the last problem. That was constant speed. Now we're accelerating the box. And in order to have acceleration, the applied force needs to win, or at least one of the forces needs to win. Right? In this case, it's the applied force that needs to win. How do we find acceleration normally? It's been a while. Remember, we take the sum of the forces in the x and we divide it by the mass. So we take the resultant force in the x. What does it end up coming out to? Now again, if this is 257.25, that's 0 net force. So you divide by 0 by 75, you get 0, right? But now the sum of the forces in the x needs to be something different. And in fact, I can find the sum of the forces in the x if I just cross multiply the desired acceleration, 0.94 meters per second squared, by the 75 kilograms. What does the sum of the forces in the x need to be? 70.5 newtons. That means not that the applied force is 70.5 newtons, right? But 70.5 newtons greater than the friction force. Do we remember doing this before break? All right, so what is the applied force going to have to be here?
327.75.
There's the applied force. Now, the question was how much work is done if the box is moved or pushed a horizontal distance of 7.35 meters. Again, how do we find work in class? Force times displacement. The force is now 327.75 newtons. Remember when we did number 4, it was 257.25 newtons, so less force. More force now because we're accelerating the box. Same displacement of 7.35 meters. How much work is done now?
2,406.
And then round it off to, was it 2 sig figs, I think? Yes.
24,000 joules.
Well, 2,400 joules, 2,400 joules of work done if you accelerate the box instead of just pushing it at a constant speed. So constantly getting faster and faster until you've pushed it 7.35 meters and you abruptly stop. Okay? The 2,400 joules of work done. Questions on the first part? All right, now the second part, Audrey, it says that it is still accelerated, but now it's being accelerated down a ramp angled 20 degrees above the horizontal. So we've got to take this whole picture and tilt it now. So So now instead of pushing it on a level surface, now we're taking and we're pushing the box down a ramp. So the applied force is down. Now that's not the only force obviously in play. What other forces do we have, class? Weight, which acts
into the ramp and down.
good. Weight acts straight down. So we think of it as acting both into the ramp and down the ramp. Same box, it still weighs 735 newtons, correct? But the normal force upward is no longer 735 newtons. How do I figure the normal force? By first finding the weight in the y, using the cosine of the 20-degree angle, right? We know that the cosine of the 20-degree angle right here at the top is equal to the adjacent weight in the y over the hypotenuse, the 735 newtons. So we cross multiply. How much weight in the y is there? Weight into the ramp. Yeah, 690.6 blah, blah, blah newtons pulls it into the ramp. That's also then the normal force. Okay, so I'm realizing we've got a little, no, other way? I need to lower the camera. It's having a hard time seeing because the garland is covering things. Here, we'll lower the camera so it has kind of the Kendall view. Poor Kendall, sorry, picking on Kendall. We love Kendall. Oh wow, that's quite the view. All right, so let's raise that up. Okay, so now, yeah, there we go. Now you can see the top of the board, despite the garland. Okay, all right, so anyway, weight in the y, 690.6 newtons in, 690.6 newtons up, and the normal force is what we use to find the It's a different amount of friction force now, isn't it? Because it's been angled, you get less friction. Which direction is friction going to act? Up the ramp, because we're trying to slide it down the ramp. So we need to find the friction force. Same coefficient of friction, 0.35. How much friction?
241.7.
Go and store this in the memory of your calculator. 241.73 blah, blah, blah newtons of friction. That's a little bit less friction, not a whole lot less, but a little bit less friction than we had last time. Now, the friction is acting up the ramp, the applied force is pushing down the ramp, but there's a third force in play here. What's the third force affecting the movement? The component of the weight that is acting down the ramp. We would say the weight in the x. So the weight in the y, we already found. But we still have the applied force going down, we have weight in the x going down, we have friction going up. So the applied force has help. The applied force doesn't have to do it all. At your seats, remember we're going to say that the sine, since this is opposite the 20-degree angle, the sine of 20 degrees is the weight in the x over the hypotenuse, 735. And how much, that can't be right. I guess it is right. Oh my. Oh, what's the weight in the x going to be? 251.38, blah, blah, blah. All right, go and put that in the memory of your calculator. I'm going to go memory 2 here. Now, question. We haven't even touched the applied force yet. What would happen if I didn't touch the box at all? It'd go down anyway, right? It would slowly slide down. It's almost 10 newtons more weight pulling it down than friction resisting it. But remember, we said the acceleration needs to be 0.94 meters per second squared. And with a mass of 75 kilograms, we said the resultant force had to be 70.5 newtons. Remember that from earlier. Am I winning by 70.5 newtons right now? No. Since I'm not winning by 70.5, I need to figure out how much I need still to win by 70.5. How would I do that?
Do memory 2 minus memory 1.
Okay, so recall 2 minus recall 1. I'm already winning by 9.648, right? So how many more are needed? Wrong direction. Yeah, I still need 60.851 blah 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 newtons of applied force to win by a full 70.5. Did you get that?
No.
All right, did you get the what was the number again? Hold on. Recall 2 minus recall 1. Did you get the 9.648? Okay. So I've already got that many working for me. I need a total of 70.5. So you could put this in memory, or the 9.648 in memory 3, and do 70.5 minus that amount. Because I've already got that much covered, so I don't need that. How much of the 70.5 do I still need? Subtract what I've already got. And that's where we should get the 60.85. Does that make sense now? So the applied force is only 60.851 newtons. And the displacement is only 7.35 meters. So pushing it down a ramp, a lot less work. How much work do I have to do now? Remember, along level ground, it was over 2,400 joules. Now?
147.25.
Could have rounded off to 2 sig figs, only about 450 joules of work needed, because I'm pushing it down a ramp. And it's really easy to push things down ramp, especially when the coefficient's only 0.35. Questions on this? This beautifully decorated stand is definitely getting in the way. It's all good. It got in the way before, but it was the metal was so thin it really didn't make a whole lot of difference. And now we've like quadrupled or tripled the thickness, quadrupled the thickness. And anyway, questions. It looks pretty though. I hate to take it down. I'm not sure what Ms. Morse would do to me if I took that down, so I'm just going to leave it there. All right. Sorry, video students. Questions. Questions on work. Do we see how all the free body diagrams from before tie back into work? All right. Then let's move on. Next term in your notes. Let's talk about power. As in you got that. All right. Power, here's your definition. The time rate of doing work. Power is the time rate of doing work. The time rate of doing work. Now, here's the idea behind power. If there was, let's just take one of these lab stools here, all right? If there's a lab stool here at the front of the, well, maybe that's a nice, my son can pick up a lab stool. Let me go with Andrew, because he's about to turn 2, okay? Andrew is not strong enough to pick up a lab stool. So let's suppose Andrew was going to slide it along the floor, okay? Now, I would just pick up a lab stool because it makes an awful racket when you drag it across the floor, but let's suppose I decided to push a lab stool across the floor also, okay? Andrew and I are going to have a race. Guarantee you my son could get a lab stool from the front of the room to the back of the room. He could do it. Now, how long would it take him? It might take him a little while. Number one, he'll get distracted, but even if he didn't get distracted, it's just going to take him longer, right? If we both dragged a lab stool from the front of the room to the back of the room, we would be doing the same amount of work. But because I would do it faster, I have more power, which is not saying much considering he's 2. Okay, but does that make sense? Be the same amount of work done, right? But if you can get the work done more quickly, you have more power. Power is the time rate of doing work. In that sense, then, power is work per unit time, work over time. So P equals W over T. But since work is force times displacement, we could also say power is force times displacement over time. Here's another way to think of it. Remember I said I get the work done faster? I move the box faster. I move the box with a greater velocity, right? I accelerate the box more quickly, which means I have a greater average velocity. Well, since D over T is velocity, my son and I would both have to exert, well, I'd actually get a little bit of acceleration off the bat, but once I hit my constant speed, right, I will be exerting the same force as he is because we both have the same friction to work against after I've accelerated up to speed, but my average velocity would be greater. We could also say force times velocity is another way to define power. So all three of these, this one is the textbook definition though. Work accomplished per unit time, or the time rate of doing work. But we could be able to use all three of these. Let's consider the units for just a moment. We said work is measured in the SI in joules, right? Joules per second. So power is joules per second. But of course in SI, we don't want to leave goofy units if we can help it. I say that, we're going to come across some goofy units later. But joules per second was redefined the watt. So a watt is then the unit of power. Now this is where it gets confusing. The abbreviation for watt is capital W, which is also the letter used for work. So if W is a unit, it means watt. If W is in the equation, it means work, which is measured in joules, power measured in watts. Okay? It's going to be corny, okay, but forgive me, and you can feel my wife's pain. So my wife, of course, she's married to a physics teacher, and so I come up with corny things. And so at one time I was telling her, okay, y'all know Elmer Fudd from Looney Tunes? Okay, I love you, watts and watts. I don't know what possessed me to just be goofy like that, but I'm goofy anyway. And I told her I love her watts and watts. And then I said, that's powerful love. Because watts is the unit of power. Powerful love, watts and watts, I love her. Okay, anyway, it's dumb, but if it helps you remember that power is measured in watts, so be it. All right, now, we could also measure in the US. Now, in the US, we said work is measured in foot-pounds. And it's the time rate of doing work, so it's foot-pounds per second. And since we're in the US and we don't come up with clever units ourselves, we're just going to leave it as foot-pounds per second, which is the other unit of power. There's another unit that your book mentions, and the unit watt was actually named after James Watt, who invented the steam engine. And so James Watt discovered if I can blast enough steam, the steam can cause a gear to move, and the gear can move other gears, and I can actually cause something to move just by blasting enough steam at this contraption. So he invented the steam engine. You might remember that from US history, world history, things like that, as you learned the different inventors and inventions, contributions they made during the age of industry. So he was an American, which is unique because most of these have been foreign guys, either Englishmen, a lot of them Englishmen, some German guys, you know, people like that. Watt is actually named in his honor even though he was an American. And as an American, he had been using foot-pounds per second. So the direct equivalent from horsepower, which was a term James Watt coined, he said, hey, my machine can do the same amount of work as X many horses. He said that an average horse, if you hook him up to a pulley system and have him start walking, every second that horse as he walks is going to lift 550 pounds off the ground, 1 foot every second that the horse walks. That's a typical horse. That's kind of what James Watt came up with. So 1 horsepower is equivalent to 550 foot-pounds per second. It's very rare that a unit is defined in terms of the US, but it's because Watt was an American. Amen. 550 foot-pounds per second, that's a horsepower. Well, the watt is the SI unit, right? Well, what's the SI equivalent? It's not perfect, but it's approximately, a horsepower is approximately 746 watts. A horsepower is approximately 746 watts. So you need to know this for horsepower. Now, clear the air, okay? A 350 horsepower motor under the hood does not mean that your car can do the same work as 350 horses, because horses don't run 70, 80 miles an hour, okay? It's not a perfect equivalency, all right? Or the little horsepower lawnmower engine. I learned a little something about those when I was in high school. I did lawn jobs in my neighborhood, and my dad had this really old lawnmower. I call it the Ramblin' Wreck. And because it made noise as you mowed, and it just kept on going for a long time. Rusty old thing, cut grass great, and finally, though, it gave up the ghost. And my dad was not buying a new lawnmower. I'm the one making money with his lawnmower that just died. So who's buying the lawnmower? I'm buying the lawnmower out of my profits, right? So this is where we learn about net profit and expenses and overhead. Overhead was I had to buy a new lawnmower. And so I bought a new lawnmower on cheap, right? So I buy the cheapest lawnmower there is. And it's got this 3.5 horsepower motor. I've been able to cut through it was like a bush hog. The Ramblin' Wreck could go through anything. And this tiny little black lawnmower I bought, Like I had to go across lawns twice, like cut it at the high setting, go through the lawn, lower the blade to the normal setting, and go through it again. It was pathetic. And then finally my dad gets another lawnmower given to him by his dad. It's a high wheel lawnmower. It was 4.5 horsepower. Large rear wheel, much easier. So I was able to use that. And so I liked that one better. And I was like, oh, there's a difference in the horsepower of the motor. But again, it still doesn't mean this is the same as 3.5 horses chomping grass. Okay, it's not a perfect equivalency, but it gives us a rough idea of how much power is there. Okay, so horsepower is how many foot-pounds per second? And approximately how many watts? 746. Look at page 163. Page 163. And let's look at the example problem 11.3. And read the example problem for us if you would, Michael.
A car is traveling at a speed of 80 feet per second. The thrust of the driving wheels against the road is 650 pounds. If power losses in the drivetrain are neglected, how much horsepower is the engine producing?
All right, so again, there's a lot of friction in the drivetrain of the car, right, where the drive shaft and the wheels, gears, all that work. Okay, but we're ignoring all of that, okay? All we're saying is the wheels push against the road backward, 650 pounds of thrust, if you will, 650 pounds of force. Obviously, the reaction force, the friction, then pushes the car forward. And it's traveling at a speed of 80 feet per second. Whatever that is in miles per hour. I'm too lazy to do it. So, how much horsepower? Well, to find power class, power is defined as the time rate of doing work. So I could use work per unit time, except they don't give me time and they don't give me work. I could also define it as force times displacement divided by time. And they give me a force, but they don't give me a displacement, nor do they give me a time. I could also find it by multiplying a force times a velocity or speed. That they give me. So which equation am I going to use?
Force times force.
Again, the key, with having 3 different equations, and you two are familiar with this from pre-cal, right? Where we had the linear velocity was defined 3 different ways, right? You had radius times angular velocity, you had arc length over time, and we had r theta rad over t, right? So we had 3 different ways to define it, just depending on what we were given. Similar idea. Kendall, if I just lost you, don't worry about it. The point is, when you've got 3 different equations, you pick the one that works best for you. The 80 feet per second is clearly a velocity or a speed, more accurately, and the 650 pounds is a force. So clearly we want the force times velocity. All we do is multiply. And that's all they did. They multiplied 80 times 650, and they got 52,000, which is already 2 sig figs. So they have 52,000, now notice, foot-pounds per second. But that's not what the problem asked. It said, what horsepower is the engine producing? If it takes 550 foot-pounds per second to make a single horsepower, how would I find 52,000 foot-pounds per second in horsepower? Divide the 550, because it takes 550 for each horsepower. So you take the 52,000 divided by 550, and it comes out to how much horsepower?
94.54
Yeah, 94.54545454 and so forth. We're going to round off to that is just the 2 sig figs. So we'll say 95, and again, horsepower is just HP. Not as in Hewlett Packard, but as in horsepower. Right. Questions on example 11.3. All right, turn over to page 171. Let's take a look at a few more problems here. Page 171, read problem 6, if you would, Audrey.
An airplane weighing 11,000 newtons climbs to the height of 1.6 kilometers in 9.8 minutes. Calculate the accomplished power in horsepower.
Now we're only looking, to be fair, we're only looking at the vertical rise. Because question, if we ignore air resistance, because we always do, even though air resistance is critical for the plane to even get off the ground, right? We understand that. There's really nothing resisting the plane's forward motion, is there? But resisting the plane's upward motion, of course, we have what? Weight, gravity pulling down against it. The weight of the plane is what has to be overcome. So the real work done in the engines isn't even that which drives it forward per se, right? Because there's really nothing resisting after you get it in motion, right? So what we're looking at is how much horsepower was required to get the plane off the ground that distance. Again, there was a certain amount of force required to start it moving and such, but how much power and horsepower to get it to reach that height? So they give us 11,000 newtons, class. That's the weight of the plane. And if that's the weight of the plane, that's also the upward force necessary to get it off the ground, correct? So this is the, if you will, the applied force upward in the y necessary to cause it to leave the ground. It says it climbs to a height of 1.6 kilometers. What's that? It's the vertical displacement. It's the displacement in the y. It says 1.6 kilometers. Kilo means 1,000. So it's really 1.6 thousand or 1,600 meters. Or you can just say move the decimal 3 places. All right? And then it says in 9.8 minutes. Of course, the class, that's time. And there's no x or y component, remember, to time. But 9.8 minutes, thoughts? Yeah, we don't do minutes. We do seconds. So how many seconds is that?
588.
All right, now the question is how much power was needed. There are 3 equations for power. Give me one of them, Audrey.
Force times velocity.
I can give you another one, Michael.
FD over G.
And the last one, Audrey.
Work.
Again, this one's the definition. Work accomplished per unit time or time rate of doing work. But if I've got a force, a displacement, and a time, class, which of the 3 do I want? The middle one, the FD over T. So we're going to take the FD, 11,000 newtons, times the 1,600 meters of displacement, divide that by the time. And again, I know this isn't a perfect analogy because there is forward thrust, okay? Whatever, and there's technically acceleration to get off, and it's not consistent, consistent power generated throughout, but we're approximately how much power was needed to get the plane this high off the ground.
29,000.
All right, and then we would round that off to 2 sig figs, except I don't need to, because the answer isn't this many watts. Remember, newtons times meters per second. That's going to be watts, okay? Because a newton meter is the joule per second. That's your watts. The question asks for the answer in watts. It asks for the accomplished power in horsepower. Now, remember, a horsepower is not defined as 746 watts. It's approximately. So if I had, say, 4 or 5 sig figs in these numbers, the 746 would limit me to 3. I'm already limited to 2 anyway, okay? So given the numbers they gave me. So we're already going to be limited to 2. But if it takes about 746 watts to make 1 horsepower, what do I do with this number? Divide the 746, and we get approximately how much horsepower to get it off the ground to that. 40.123, but rounded 40 horsepower. And again, that would be total horsepower. It's going to require a lot more power initially, right? Getting it up, accelerating it up to the speed necessary to get it off the ground and all of that. So again, I know this isn't a perfect problem, and whatever. It gives us the idea of how to use the equation. Questions on this? And I just realized I was covering up half of that. Sorry, Kendall, that's the work. Hopefully you followed what I said. All right. Anyway, number 7. Go and read that for us if you would. Michael.
A hopper of concrete hoist weighs 3,100 newtons when half loaded. If this hopper is raised 55 meters in 6 seconds, find the power required in watts and horsepower.
All right. What's a hopper? Ever heard of that before? A hopper? Okay, have you ever noticed you ever sat at train tracks and watched train cars go by? You ever notice that on the bottom of the train cars is a sloped thing with a valve underneath? Those are called hoppers. Okay, so a train car usually have 3 or 4 hoppers on the bottom. It's for putting gravel, sand, that kind of substance. I guess they could put liquid, though they usually put those in tanker cars. And so what they'll do is they'll actually put the hopper over whatever container it needs to be in, open up the thing, everything drains down out of it. Well, a crane can oftentimes use a hopper, for instance. If you wanted to dump a bunch of something into it, you could move the crane, open up the bottom, and everything comes down out of the surface. Okay, so a concrete hoist, it's hoisting up this thing full of wet concrete, dropping it down. I guess the concrete mixer truck, the cool ones that spin on the back, that one wasn't going to be good enough. So they put the concrete into a hopper, put it where it needs, for instance, in building a high-rise. Right, you put the metal waffly grid work down for the floor, and you pour like 5 to 10 inches of concrete on top of it. Now you've got a nice, strong, sturdy floor. Okay, so that's kind of what we're doing there. Anyway, that's neither here nor there. Just thought I'd mention that. So we knew what we were talking about. The hopper weighs 3,100 newtons. Right, that's weight. And if it is, assuming it's like a crane, right? So you got the crane. All the counterbalancing weight, you got the long boom of the crane, and you got it. Okay, so there's the hopper, there's the valve at the bottom. Okay, if it weighs 3,100 newtons, then that means the upward force, which is actually a force of, since it's in a cable?
I think so, tension.
Tension, right? The tension is the upward force here. The tension also would have to be 3,100 newtons if it's pulled at a constant speed, right? So we'll assume the applied force or the tension force here is the 3,100 newtons. It's raised 55 meters, class that's displacement. And it's raised that high in 6 seconds. Time. At your seats, finish the problem. Like my artwork, Audrey? Just to compare with last year's fireplace. I was thinking I can't do fireplace this year. I need both boards in my upstairs room. Just didn't need it last year. Notice they're looking for 2 answers. They want the watts, watts and watts of watt. They want the watts and they want the horsepower. Kendall could be a nerd and tell her daddy, I love you, Watts and Watts, daddy. See what he does. But I get a rude Facebook message from him if you did that. You should try it. Not work, power. All right, what was the power in watts, first of all? Michael?
218,416.
All right, now we did want that answer, so we need to round it off to, which is 28,000 watts. Or you could say 28 kilowatts. Wait a second. Watts, kilowatts, power, like power bill, yeah. All right, that's analogy. But they generate power, right, at the power plant, either through coal or natural gas. In some cases here, hydroelectric dams generate power. Anyway, and they wanted that also in horsepower. So, Audrey, how much horsepower is that?
38.09.
And then round it off to the 2 sig figs.
38 horsepower.
Almost exactly 38 horsepower. All right, did we get 28 kilowatts and 38 horsepower for our answer? Good. Take a look at number 8. This is kind of an interesting problem. Read number 8 if you would. Audrey.
Elevated car with 6 passengers weighs 5,600 newtons. A, calculate the power required to raise the car at 1.8 meters per second. B, if the cables holding the car run over pulleys to a total counterbalancing weight of 2,400 newtons, what power is required from the elevator's motor?
All right. So for starters, we got elevator car, 6 people in there. Of all different sizes. Somebody's feet are sticking out the elevator. And it's connected to a pulley that lifts up, right? So there's tension force needed. How much tension force is needed to pull upward on this elevator?
5,600 newtons.
5,600 newtons needed, because that's the weight. of the elevator when it's got these passengers in it. And it says it's pulled at 1.8 meters per second. What is that? Speed. Or we could say velocity upward. What equation should we use to find the power? P equals FV. Force times velocity. Really straightforward. You just multiply. He didn't ask for horsepower this time, did it? Ha, we're off the hook. All right. How much power is needed?
2,080 watts.
Round it off to 260. Oh man, I'm not off the hook. I'd be off the hook if they had horsepower.
10 kilowatts.
Oh, I like it. 10 kilowatts or 1.0 E4 watts. Either of those would be not. But I like the 10 kilowatts. Nicely done. That's if you just had a motor at the top that was like a winch, if you will, causing this elevator to go up. That's a lot of power needed, right? So instead, what you've got is you've got the motor that's turning the shaft, you know, the little gear teeth or whatever, the cable, but you've got a weight going over the pulleys, if you will, and there's counterbalancing weight down here, 2,400 newtons. Now, if there's 2,400 newtons here, that's weight pulling down. That force is transmitted over here, and there's already 2,400 newtons of tension pre-existent before you ever load up the elevator and start it moving. Presumably, that's approximately the weight of the elevator unloaded, but we don't know that for sure. All right, if that's the case, how much additional force is needed to hit the 5,600 Newton mark? How much force does the motor have to put out? 3,200 newtons. The motor only has to produce 3,200 newtons of force. Same velocity, now how much power is necessary? Only 5,760 or approximately 5.8 kilowatts or 5,800 watts of power if you use the counterbalancing weight on the other side, which is a really smart idea. All right, questions on that? All right, 2 parts to your homework. First of all, study pages 158 to 163. Study pages 158 to 163. And complete a handout. It's in the description of the video. Just a couple problems here, all about work and power. That's the first part of the homework. We're going to have a quiz in our next lesson over work and power. Study those pages, do that handout. We also want you to preview the next section that we'll be looking at tomorrow. So also read pages 163 to 165. Also read pages 163 to 165. And on page 171, answer questions 12 to 15. Page 171, answer questions 12 through 15. That'll preview what we're going to start talking about in our next lesson. Have a wonderful rest of your day, and you are dismissed. Kendall, hope you get feeling better, or Mom gets feeling better. Hope you're able to rejoin us soon.